So Nitya is a student of UFA, and today she'll tell us about coloring graphs and.
Hi everyone. So today I'm going to talk about some joint work with Zongchen, Kukui, and Encore, establishing strong spatial mixing for colorings on trees and its application to approximate sampling and counting. So I'm going to first start by trying to define all the words in the title and explain to you why I think this problem is interesting and beautiful. As I go through the talk, please stop me if you have questions. One of the reasons I'm giving a chat talk is so that I don't run through the whole material before anyone can read anything that I've written. So what's the setup? The setup is that we have some graph, and the graph has n vertices, and we'll think of n as very large, going to infinity. And this graph is a bounded degree graph, where we think of the maximum degree as like bounded, but like large. It doesn't have to be bounded. In fact, it can be 3, but I think that's like kind of the right picture to have in your mind. And the task that we're going to do is we're going to color all of the vertices of the graph with one of q colors. We'll just number the colors 1, 2, all the way to q. And we want to consider only proper vertex q colorings so that they have the property that if I have 2 vertices and they're connected by an edge, they receive different colors. So let me let omega be the space of all proper vertex q colorings of G. And one question we're going to try and answer is like, what can we say about how big this set is? If I'm just given an arbitrary bounded degree graph, delta. A related object, and in fact, the primary object that we're going to study in this talk is a distribution. So it's mu, which is the uniform distribution over proper q colorings. And so the question that we're going to ask is like, what can we say about this uniform distribution over proper q colorings? What kinds of nice properties does it employ? Can we efficiently approximately sample from this distribution? And what properties of mu make it possible for us to succeed or fail? Now, importantly, because this is the question we're going to be studying, the regime that we're going to work in is where the number of colors we have is always at least 1 plus the maximum degree. And why is this the case? Well, in the positive direction, if I have at least as many colors as this, I can always find a proper q coloring. And how can I do this? Well, I can do it greedily. So I take some vertex, I color it some color, maybe I color it red. Then I look at one of its neighbors, and I can color this thing anything except red. And because this neighbor and every vertex has maximum degree delta, if I try this greedy process, at every step, there's always at least 1 color that I haven't yet used. In the converse direction, right, if I have not this many colors, it might be the case that there is no proper q coloring. For example, if I take a clique. And in fact, we can say something stronger is true, which is that when q is less than delta, trying to approximately count or sample q colorings is hard. So this is due to kind of 2 works, 1 old and 1 new. And it's hard in the sense that unless NP equals RP, I'm not going to, for the purposes of this talk, we'll consider anything of this type to be hard because we're only going to work on problems that are easy here. And so we're kind of going to assume this minimal necessary condition as I kind of go through the talk. Okay, so what are the kind of motivating questions that we're going to try and answer? So there are going to be 3 motivating questions. The first question is, when can I efficiently approximate the size of omega? So when can I efficiently compute how many q colorings there are approximately? The second motivating question is, when can I efficiently approximately sample from mu? So it turns out that these 2 questions are essentially equivalent due to a property called self-reducibility. This is not so important for this talk, but you can imagine that if I could efficiently count the number of colorings, because like kind of the property of being a maximum degree delta graph is kind of closed under taking subgraphs, I could also estimate marginal probabilities, the probability that a vertex is, colored some particular color by like counting how many colors where it is some color and counting how many colors where it's, all of the different possible colors, and then deleting it, making some adjustments. Like I said, this is not very precise, but the important thing is that kind of efficiently approximately counting is similar to efficiently approximately sampling. So the third question I'm going to state is not going to necessarily sound like, the first 2 questions, which is when does this distribution mu exhibit decay of correlations? So what do I mean by this? What I mean is that, okay, what would be a graph where it'd be really easy to sample for, proper coloring? Imagine my graph is just the empty graph. So I just like n vertices and I have like no edges at all. Then it's really easy for me to sample a uniformly random proper vertex color, right? I could just like take every vertex. I could like independently choose a color. And whenever I do this for all my vertices, I get a proper Q coloring. Now this is like, clearly not true if my graph has some edges. But decay of correlations is saying that like, hopefully something approximately like this is true, which is that if I take, some vertex V and I look at some really, really, really far away vertex W, if I color, V red, or if I color V blue, neither of these has very much effect on the probability that W is any of its possible colors. And this is kind of what I mean by decay of correlations, which is that like kind of nearby some vertex's V color could have an effect, but far away from that vertex, it doesn't have that effect. And you might imagine, that knowing that mu is like close in this sense to a product distribution would make it easier to sample. And I think this is like really one of the like really driving motivating questions in approximate sampling, and the corresponding area of statistical physics is trying to make this notion rigorous, which is, can we kind of draw some kind of arrow like this between this first set of regime and the second kind of regime? Now maybe I'll state a little bit more notation, because as you've heard, I'm talking a lot about what the induced distributions are on specific vertices. So I'm going to let mu sub v be the marginal distribution on some vertex V, and I'm going to let mu superscript tau be the conditional distribution. And what this is that tau is going to be some partial assignment, which is like I tell you the colors of some vertices, and now I look at like sampling from the uniform distribution of all the remaining colorings that agree with tau. Distribution given some partial assignment, which I often call a pinning, because we pin some of the vertices. Okay.
Some people actually call it link, but
I think a lot of things in this field have many names, some old, some new, and they're often, I think even like these notions of decay of correlations get so many names. Okay, so let me tell you a little bit about like what might be one way to make this phrase precise and one way you might hope to efficiently sample. So let me start by telling you, how might you hope to efficiently sample? So speaking of things that have multiple names, one of the most classical ways to sample from distributions like this. So what is this distribution? It's like a distribution where like the size of the sample space is exponentially big, and we don't even know how big it is, right? We don't exactly know how big omega is. And so a common way to try and sample from these distributions is often called Gibbs sampling or Glauber dynamics, which is just that you run a Markov chain that makes local updates for hopefully not too many steps. And then when I spit out, I hope that whatever I spit out is close to the uniform distribution. So what do? I start with my favorite coloring. In fact, it doesn't even need to be a proper coloring, but we already know we can make a proper coloring. So I start with some, proper coloring. And I'm going to repeat the following process. So from 1 all the way to t, I'm going to first randomly sample a vertex. And the second is I'm going to update only that vertex. So what are the possible colors that this vertex can be? Well, anything that its neighbors aren't. So I'll randomly choose a valid color. And I'll keep all of the others, xt plus 1 of w, all the others are going to just stay the same. And eventually, once I run this for t steps, I'll return, my coloring x capital T. And the hope is that, this law of this, random coloring I spit out is close to the, uniform distribution over proper colorings. And in what sense do I mean approximate? Well, I think the kind of classical notion to compare two distributions, there are many ways to compare them, and it doesn't actually matter too much which one we use, but is the total variation distance. So the total variation distance between two distributions. So I'll denote it by mu minus VTV, or I might just write DTV. So it's just like 1/2 of the L1 distance. So I look at all of, my possibilities and I compare what the probabilities are in these two distributions. In fact, the TV distance is not so nice to work with in many ways. And so we'll often discard it in favor. In fact, a lot of this talk will be discussing ways we can discard the TV distance in favor of a more better behaved distance. But how can we think about, how long we're going to have to run this, Markov chain for until we can hope reasonably that what we get out is close to mu? Well, one necessary condition is that we should probably at least try to resample every vertex once, right? Like if we don't even try to resample some vertex, probably it's not distributed like the uniform distribution. It's just distributed like whatever the initial coloring is, because we, haven't even bothered to update it. And so by the coupon collector problem, we need T to be like at least like n log n, right? Just in order to even sample every vertex once, we need it to be order n log n. And kind of a really beautiful thing is that for a lot of these classical problems, this very simple necessary condition turns out to be essentially sufficient, which is once we're like resampling each vertex a constant number of times, that's already enough for whatever we spit out to have distribution close to the uniform distribution. If you're like paying very close attention to what I'm saying here, you might notice that we might, in order for this to have any hope of success, we need to make this 1 and 2. I'm not going to worry too much about these sorts of things, but
it might not be even connected, right?
Yeah, so that's why you need to make this a 2 in order to get connectivity.
So once it's connected, it's enough.
Yeah, and I guess kind of that kind of is like probably one of the most famous open problems in this setting of approximate sampling and counting is the kind of conjecture that, as long as the number of colors I have is like delta plus 2, so that like I can have at least 2 choices here, then, that's enough.
You meant it's not that it's enough.
It's not enough.
It's not really some concept factor. Probably should tell us.
Yeah. Okay, actually, I don't know if this space is much good for anything. So so I've told you a little bit about how we might hope to sample. Yeah, so we want that we can run this, and then if we run different n log n steps, our goal is that we converge to the uniform distribution.
For infinite time.
Yes. Yeah, so in infinite time, you can show that this converges, as long as Q is at least delta plus 2. And the question is, can you show in n log n time or in polynomial time that you can get something that's close? Okay. So now that I've told you a little bit about what sampling might mean, let me tell you a little bit about what decay of correlations might mean. And in order to do this, I'm going to use a notion that's very commonly studied recently in the sampling literature, but maybe comes more classically from statistical physics. And that's the idea of weak spatial mixing and strong spatial mixing. So let me start by defining weak spatial mixing, which I will define with a picture. So suppose I have some vertex R, and I look from the perspective at R, and I let these be all the vertices that are distance k away from R. So these in the graph are distance k away from R, and I have some vertices. I'm going to make an identical copy of this picture here. This is about the limit of my artistic skills. So these are just 2 copies of the exact same graph. And what weak spatial mixing says is that suppose in this left-hand copy, I color all of the vertices that are distance k away with like some set of colors. I'm just calling them all red for simplicity. And on this right graph, I color them, something different. Whatever. I make some 2 different choices of coloring of the vertices distance k away.
Legal.
Pardon?
Legal color.
Yeah, legal. I make 2 legal choices, although, so I make 2 legal choices of coloring. And the question is, what effect does just knowing this have on the marginal probability that, let's say that, that R is colored yellow? And the point is that we'll say that a distribution has weak spatial mixing if the marginal probability, the difference between these two marginal probabilities, is decaying exponentially in this value k. So more precisely, I'll say that a distribution has weak spatial mixing if I take any two, kind of partial assignments, and I have the property that the TV distance, if I take some vertex v, I'll lift up R actually to be consistent. If this thing is decaying, and this means up to a constant factor, at some rate that is exponential in the distance between R and the pinning, like the distance between R and the nearest vertex. So in fact, these could be distance all at least k. But it's just decaying exponentially, this kind of distance. And you can see how this is a notion of correlation decay, because this is saying that the effect that assigning vertices a color can have on R is decaying exponentially in their distance to R. One important consequence is that the only way this can be true is if no matter what this pinning is, eventually as this pinning gets further and further away, the marginal probabilities of all of these colors become 1 over q. That like kind of no matter what I pin, as long as it's far enough away, basically the marginal distribution on this root vertex is the uniform distribution. Now I say this because I'm about to define a different notion, which is the notion in this talk, which has the word strong in it. And to define strong spatial mixing.
This is related to the Bruges-Schlossman type argument, right?
Yeah. So to define strong spatial mixing, I'm going to actually just cheat and use the same diagram again. So strong spatial mixing is similar to weak spatial mixing, but it has the following caveat. And the caveat is that I'm allowed to actually pin or color nearby vertices to R. Except that on the left and right side, I have to color them exactly the same way. And so we say that a distribution has strong spatial mixing if it has this stronger property that the difference in the marginal probabilities is not just decaying exponentially in the distance to a pinning, but is rather decaying exponentially in the distance to where they disagree. So it's the distance to the disagreements with the pinnings. And a different way to think about this is to say that a distribution has strong spatial mixing if all of its conditional distributions have weak spatial mixing. So this is like some stronger property that is believed to hold. So let me.
That definition is new.
Pardon? No, this is a very classical and well-known definition, right? Which is that a distribution mu has strong spatial mixing if kind of for all pinnings, I'm going to copy the same thing. So for all tau and tau prime that go from lambda to q, I have that the TV distance is decaying like 1 minus delta, but now this is to the distance from V to where these disagree, which I'm going to denote by this partial sign. So it's not just to where the first vertex is, but it's to the first place where they disagree. So you can see that strong spatial mixing implies weak spatial mixing. A kind of surprising thing that has turned out to be true in a lot of cases is that it's widely believed that the point at which weak spatial mixing starts to hold is essentially the same as where strong spatial mixing starts to hold for many natural distributions. Like I said, there are lots of caveats, so I'm not going to make an absolute statement, but this is known, kind of black box, almost literally nowhere. And it just happens to be that kind of we'll have two different proofs and they'll coincide, but it's kind of believed statistically that there's kind of one phase transition where both of these kind of start to hold.
This phase transition is on the structure of the graph itself, or?
So this is a good question. So this is on the structure of the distribution.
Oh.
So both of these are properties of the distribution, where the distribution goes, you can imagine from having product-like behaviors to not having long-range correlations. Okay. So motivated by these definitions, let me tell you kind of a few conjectures. So the first conjecture is, like I said, perhaps the most famous conjecture in this area of approximate sampling and counting, which is that when Q is at least delta plus 1, we can approximately sample from you. And like I said, if you want this Glauber dynamic strategy to work, you might need to replace this 1 with a 2. The second conjecture is going to sound like it's very surprising that we don't know it, which is that the uniform distribution mu has strong spatial mixing on all maximum degree delta trees. So not general bounded degree graphs, but just trees.
The degree down
Yeah.
or the degree?
Delta is the maximum degree.
Okay, yeah. So if you draw it from a vertex, you have branching factor delta minus 1.
That's right. And I mean, it also holds on the D-area tree too, but I think it's, like I said, I'm not going to fuss too much about the small plus or minus 1 constants because you do get slightly different versions. Okay, so this is kind of conjectured. This is still open, or was still open. And the third conjecture is maybe the most surprising conjecture, which is that 2 implies 1. I.e., if we only knew strong spatial mixing on just trees, that would be sufficient to have a sampling consequence for all maximum degree delta graphs. Okay. So this is maybe these are all folklore conjectures that have been said many times over the last 20, 30 years, but it's maybe surprising that conjecture 2 is even a reasonable conjecture that one might make. And so maybe let me tell you a little bit about some previous work towards these conjectures. So the first thing is that there's been a really long line of previous work, so I will not give an exhaustive list of all of the previous work in this area, but I will give some attempt to at least characterize a little bit about what's been studied. So on the sampling side, and you can think of sampling as kind of mixing in time, and you can think of correlation decay as like mixing in space. So on the sampling side, what kind of very classically, maybe the first big progress came when Jerome in 1995, I think, showed that when Q is at least 2 delta, this Glauber dynamics algorithm mixes efficiently, which you can see this by path coupling, by showing that at every step, there's a coupling where you on average make progress. And this was improved by Vigoda in 99 to show that when Q is at least 11/6 delta, a slightly different Markov chain called the flip dynamics, where you can imagine you kind of change the colors of many vertices at a time, means that you can approximately sample from the uniform distribution efficiently. And you can see that there's going to be now a very big time gap, which is in 2019, 20 years later, this was improved to 11/6 minus some very tiny epsilon 0. It's a very beautiful result, but this is essentially where we're stuck in terms of sampling from general graphs of maximum degree delta. And so a very natural question is, okay, maybe this is really hard, we really can't sample from, yeah?
Sorry, can I ask, is it true that now it's known that Glauber dynamics also gets this 11/6?
Yeah, I think so, because now we have spectral independent. We know that spectral independence holds. So we also, and then we know that some property holds of the distribution when Q is at least 11/6 delta. And there's this really nice result that tells you black box, when a certain type of correlation decay called spectral independence holds, then we get a sampling consequence. Okay, and so you might hope that maybe we can make more progress towards sampling if we put some restrictions on the graph. And so you might imagine that the kind of restrictions you put are restrictions that kind of, trees are pretty easy to sample Q colorings from, right? You can do this by dynamic programming. So you might imagine that restrictions that make the graph more like a tree make it easier to sample from. So what's known in this area? So the best known for sampling from triangle-free graphs is when Q is at least 1.76 delta, which has been shown independently and roughly concurrently by several groups of authors as a consequence of a variety of different kind of work. You can see we make some progress. This is smaller than 11/6. And perhaps more importantly, the other question right here, just so I cite all the authors correctly. But you might, kind of ask a different question, which is like, this is saying with a minimal condition, how much better can we make? You might kind of ask the converse question, which is how much of an assumption do we have to make to be able to go down at least to like 1 plus epsilon times delta? And the only regime where this is known for is due to Hayes and Pagoda, who showed in 2003 that Q at least 1 plus epsilon times delta suffices if the graph has girth at least 11. So the shortest cycle has length at least 11, and the maximum degree is growing with n at a rate at least log n. And this condition is actually really important because it means a totally different set of techniques works, where you can roughly go vertex by vertex and try and sample by some rejection sampling type of argument. So this is actually like, in some sense, might not look like a really strong condition, but it kind of allows some very different techniques to work that really don't work, because like the kind of conditions they assume are false. And this is kind of the only regime, or the strongest regime, where it was previously known that you can sample close to the conjecture threshold. So now let me tell you what was known about spatial mixing on trees. So maybe given that it's so easy to sample on trees, you might think that people have known how to establish weak and strong spatial mixing on trees for a long time. And the kind of answer is, surprisingly, this is not true. So in 2002, Jonassen showed that trees, so these are all about trees, that weak spatial mixing holds on trees when, exactly up to the conjecture threshold, where Q is at least delta plus 1, and his proof proceeds by a reduction to graphs of trees of at most like 1,000 vertices, and then uses a computer program to solve from there. However, in terms of when strong spatial mixing holds, the best known result is from previous results from 2019. And in 2019, it was shown that strong spatial mixing holds when Q is at least 1.59 times delta. And sampling is easy for trees. So this is kind of surprising that this is a pretty basic question about the uniform distribution over colorings on trees, and yet kind of it's been quite difficult to get the answer to this question.
Even for Q equals 3 and binary 3.
I think for Q equals 2 and 3, more is known, and maybe even 4. For 4, more is known. In fact, this is a really excellent question, because let's come back to the Q equals 2 case. The Q equals 2 case, I think, provides the strongest evidence for this conjecture of conjecture 3, which is it's known that not just for 2 colorings, but in general for more general 2 spin systems, where you say like, how much do I like having neighbors that are color 0, 2 neighbors of color 1, or 1 of 1 and 0, if I can specify my favorite matrix for those interactions, those 2 spin systems are essentially perfectly understood. And in fact, this kind of idea works, in generality for 2 spin systems via this reduction of White's and Scott-Sokal known as the self-avoiding walk tree, where you can construct, given a graph of maximum degree delta, some auxiliary tree, which is the tree of self-avoiding walks, and using kind of strong spatial mixing on the tree, you can conclude your favorite sampling consequence about the associated graph. And so that's perhaps the strongest evidence that this is like a reasonable thing that one might hope is true. Unfortunately, if you try to kind of prove, kind of very naively, a similar result, what will happen is that the tree you'll get will kind of have degree that explodes. The degree will kind of scale as Q times D. So it won't really be the case that kind of results on maximum degree delta trees tell you anything about results on maximum degree delta graphs. You'll lose some bad factor of Q somewhere in the middle if you try and do it naively. So the main work of this talk that I'm talking about is kind of to try and make some progress towards this kind of agenda of conjectures by essentially resolving conjecture 2 and showing how you might be able to do something towards conjecture 3 if you put some restrictions on the graph. So let me say the main results, and then for the rest of the time, I'll tell you a little bit about how the proofs of the main results go. Getting a workout.
Something about the graph itself being an expander or high girth or something, is it?
So when a graph is high girth, like there are various results. This is still the weakest result where we can get all the way down to 1 plus epsilon times delta. With weaker girth conditions, you can get like, if the girth is,
Stronger, like if it's logarithmic girth or if it's an expander.
yes. So,
How much does it mean?
Okay.
Yes, it's something else.
so if the girth,
If it's not, if it looks like an expander Cayley graph has locally as a tree, right?
yeah,
Oh, no, it depends on they are not necessarily, they are expanded with small cycle.
But I'm asking about.
You're asking about, yeah.
so if it has really high girth, then, well, a great example is a tree. So we still don't know, we didn't know strong spatial mixing on trees, which has like infinite girth. But you can, from the strong spatial mixing result on trees, pretty quickly black box conclude a sampling result on all log n girth graphs. The thing is that our graphs we're kind of considering to have like not so big maximum degree, because the maximum degree is really big, different methods work. And so there is like not that many interesting graphs that have like log n girth and like bounded maximum degrees, just kind of not a very.
I know.
Yeah, but I mean, I think that like kind of, yes, I think our results, because it was not done for trees earlier, our results will imply sampling consequences for high girth graphs, but also much lower girth graphs, as I'll tell you in a moment. Expanders are actually generally harder to work with for these kinds of results than are like amenable graphs, which are graphs which have bounded expansion. Some of these results kind of extend a little bit, they give you something slightly stronger if you're able to upper bound the expansion of the graph, actually. Because you just kind of bound how many neighbors can cause problems for you, so how quickly your kind of disagreements propagate out of control. Okay, let me tell you a little bit about the main results, which include a result about graphs of girth, a result about. Okay. So our first main result is that if we have Q, if we have delta, which is at least 3, delta at least 2 is known for other reasons, and Q is at least delta plus 3, then the uniform distribution has SSM for all trees. So this is essentially resolving conjecture 2 of max degree delta. And our second main result, I should say main results, since I erased their names, let me. And the second main result is like towards this kind of sampling consequence, which is that whenever delta is at least 3, if I have girth, at least, so I have girth, which is like constant but scaling with delta. So if graph G has girth yes, thank you, at least some constant that scales with delta, then kind of Glauber dynamics mixes in order n log n time. So this is like essentially optimal. In the same parameter regime, where Q is at least delta plus 3. And just to give you a little bit of a sense of like, so this is a constant girth condition. So it's, and just to give you a little bit of a sense of how like, this is like not like a super crazy dependence that I've hidden here, I'll just state a slightly weaker version, which is that we get sampling when Q is at least 1 plus epsilon times delta, when the girth is like order log squared delta. So it's a relatively weak dependence on the girth that we have in order to get a sampling consequence.
Your girth has to be at least as big as.
Yeah, so this is like a lower bound on the girth, but we have no. Yeah, so the important thing is it's a girth condition, and there's no condition on the degree, and the girth condition is constant. So it doesn't scale with the degree of the graph. It doesn't scale with the number of vertices of the graph. And it's not super terrible either. It's not like I'm secretly hiding an e to the delta somewhere. It's like a relatively reasonable condition. So for the rest of this time, I'm going to try and tell you a little bit about how the proofs of these two results go.
Is there a big constant in the big omega log squared?
Yeah.
There's some constant. I mean, I think at the expense of making this a little bit weaker, this constant is like very reasonable. Like maybe like 5 or something. If you like, maybe if you get like, like there's some dependence, but if you're allowed to, if you want to mix it like 1.1 delta, this will be pretty reasonable. It's like log 1 over epsilon, so it won't scale too badly. Does anyone have any other questions about the statements of the results? So let me tell you a little bit about how we prove them. Let me leave the definitions of strong spatial mixing. Or so mostly what I'm going to try and do is give you a little bit of an idea first about how might you prove strong spatial mixing. Like if I was trying to prove such a result like strong spatial mixing, what might I try to do? And one thing that's going to help us here is the following fact. So we're going to be working with trees to prove strong spatial mixing. So suppose I have some root vertex R, and I have my neighbors, V1, all the way to VD. Now it turns out, this is a very nice result, that there is a recurrence I can write down, which is if I view my tree as rooted at R, I can compute the marginal probability that this root vertex is colored C in terms of the marginal probabilities that each of these are colored C in their like subtree rooted kind of at themselves. And so what this tells me is that PR of C, which is the probability that the root vertex gets color C, is proportional to, well, it's maybe exactly what you expect, the product of the probabilities that none of these things became C. 1 minus the probability, and this is notably the probability that VI is C in the subtree rooted at VI. So you can see that we'll just say that like kind of this probability that the root vertex is C is some function, which is just like some normalized version of this, GC, of these probability vectors of each of its children. Now, I think this is like really useful for us. Why is this useful for establishing strong spatial mixing? Because what this lets us do is this lets us kind of try and make progress towards proving a result like strong spatial mixing step by step. So we might hope to show that kind of with every step we go down the tree, kind of our marginal distributions get like progressively closer and closer together, one step at a time. Okay, so what do I mean by that? What I mean is that we would like to show something like the following is true. Imagine we could prove that the distance for some favorite metric of ours between, some distribution PR and some different distribution on the root vertex PR prime was like at most 1 minus delta times like the worst case difference of the induced distributions over all the neighbors. So imagine we had some result like this.
For some distance.
Yeah. So imagine we had some result like this, then we could iterate this to get contraction. So if this distance was literally the total variation distance, in fact, we literally plug this in and we get the desired strong spatial mixing result. Unfortunately, this is false for the total variation distance in the parameter regime we care about, which is very sad. Yeah.
Can I ask something? So when you do this, I guess, okay, sorry, I'm just gonna say some stuff and then maybe it'll turn into a question.
So
it looks like in principle, what you can do is you can just on every vertex define like just two things, which is it color C? Is it not color C, where C is a fixed color, and then kind of look at every color separately, but somehow that's not okay.
Well, I think that you're saying that like, I think you need some consistency between these, and you also want some property to be held jointly by the probability distributions. Like I think the problem is like, you'll have like maybe Q recurrences, but then they'll have parameters that all feed into each other. So
No, I don't, sorry, like if I know for every subvertex, the probability that it's color C and the probability it's not color C, I can compute the probability that V is color C or not, right?
That's right.
So I can kind of run this whole thing just with like two states. Is the issue that like, in the final distance, maybe there's like one color that like contributes all the air and the rest all contribute nothing or something?
Well, I think you want to show that each of the marginals you're getting the right contraction, because one thing you can think about for strong spatial mixing is something like the following. Like you could have pinned vertices in strong spatial mixing so that the root vertex is only actually deciding between two colors. for example. And then in that case, or a very small number of colors. In that case, knowing contraction of the other colors doesn't really tell you anything. You kind of need to have contraction for each color individually. Maybe that's not quite answering your question.
I think the issue is that in the formula is the probability of a root color we see is proportional to that. So you need to.
Oh, you're just asking where does the other colors come? Sorry, I just didn't understand your question at all.
Where the other colors come into this recurrence.
Oh, yeah, it's because the formula is just, sorry, I apologize, I just didn't understand your question. Yeah, the formula is like divided by the sum over all of the colors. So like I said, I cheated, I didn't write out the whole formula here, but.
That answers my question. So
Okay.
You can't just run the recurrence with only caring about one color at a time.
There, this is the actual formula, and you can, cool, sorry, I didn't understand. Okay, so like I said, if kind of this was genuinely total variation distance, and we had this property was true, we'd be all done, we'd be so happy. Unfortunately, like I said, it's not true for total variation distance, but that doesn't matter too much. I think that the story of approximate sampling is that like total variation distance is very difficult to work with, so we try to work with almost anything else we can that's easier, like KL, L2, and it turns out that in the case of strong spatial mixing, it doesn't matter too much because we can just show contraction in our favorite distance metric and then pay a one-time cost at the beginning and end to like convert to and from the total variation distance. So that as long as we're getting exponential decay for so many steps, paying a one-time fee at the beginning and the end is not so important. Now the difficulty is, of course, how do you like find a distance metric that actually contracts? And that's maybe the tricky part. A lot of the previous literature uses something like an L1 distance, because you can see this looks some kind of like L1, L infinity. You see some like Holder-like effect happening here. And the main, one of the main ideas in our work is to use something like an L2 distance in order to make progress on this problem. Okay. So how might you use this tree recursion to prove something like this? Well, we know that these terms on the left-hand side are functions of terms on the right-hand side. In fact, they're given by this function GC. So how big this quantity is essentially saying, if I change the arguments to this function, how much can I change the output? And that's just like saying, how big is the derivative or the partial derivative matrix, which is going to be called the Jacobian, is like not very important. And I'm not going to write down exactly what the partial derivatives are, but like this is just saying, what is the size of the gradient or set of partial derivatives of this function? And so that's really what we're going to try and do, is to try and find some norm in which we can show that the gradient or the derivatives of the partial of this kind of function have small norm. In other words, let J or G J, G be the Jacobian. So this has like D times Q squared many things in it. Be the matrix of partial derivatives. Of this vector valued function G, which is like all of the color vector, we have like kind of. We're gonna want to find some norm in which
it's D by Q.
it's D by Q squared, because
each of them is a vector of Q squared.
yeah. So it's a very big, as I said, it's a very big matrix. And we're gonna take one more step, which is we're gonna convert from working with probabilities. We're gonna conjugate with some smoothing function to G. So we'll let G phi, which is, we're gonna conjugate by some function, and we're gonna actually try and bound for a similar reason to how we can pay a one-time cost to convert to and from. As long as we conjugate with a reasonably, smooth function, smooth inverse, everything like that, we can work with kind of this function instead of actually our message recursion. And we're gonna try and find some function, and our goal is to show that some suitable norm of this thing, some suitable norm is smaller than 1 minus delta. This is our goal. So let me tell you first, these are called, this function phi is called a potential. And so the potential that we use is a potential not of our creation, but a potential that was first used by Liu and Yin to study kind of deterministic counting of proper Q colorings on bounded degree graphs. And the potential that they use, So the potential I'm going to just define implicitly by its derivative, which is actually the only thing that appears in the Jacobian. And I'm going to call this capital Phi of P, which is 1 over the square root of P times 1 minus P. And like I said, we're going to work with something like an L2 norm.
This is the square which is only on the P.
Only on the P. And I'm going to explain to you why this is a reasonable choice of potential by showing what happens when you compute this Jacobian, when you apply this potential. And I think this will give a very good motivation for where this comes from and why working with this potential in conjunction with the L2 norm is a good idea. Okay, so let's suppose that I try and compute this Jacobian. Now I'm only going to restrict the Jacobian to one of the vertices, because remember that what we're trying to do here is take a maximum over I. So we'll pull that out into our norm. So I pick just one of my vertices and I can look at the matrix, this Q by Q matrix of partial derivatives with this choice of potential. And what do I get when I do this? I first get a term that looks like this. This is term 1. I get a second term. This is after some rearrangement. I get the second term. And I get the third term that I get looks like this. Now I'll explain what all of these terms are. Okay. So this is what I get. Now you're like, okay, I wrote some big expression down. Why is this making progress? Well, the reason this is making progress is because we're going to be able to control the L2 norm easily of each of these 3 terms. So let's start with the first term.
So this is just a calculation.
Yeah, but I think the important thing is that like you have to kind of construct all of these things with kind of foresight into what will make this calculation easy. So to justify why I make these choices, I'll explain what aspects, what kinds of things do you want to see that are easy to calculate with. So the first thing is that why is the norm of this matrix bounded? Well, it's a diagonal matrix. So I just want to argue about why each entry is individually bounded. And the important thing is that imagine I have some vertex V and I have some neighbors. What can I say about the probability that this vertex is color C for some color that's not used? Right? So suppose I have some color and it's not really appearing here. Well, I have Q colors and I have D neighbors. So at least how many free colors I have is Q minus D. Right? This is like a very simple bound. And in fact, basically applying this simple bound is going to be enough for us to show that this is small. Because GP is going to be at most 1 over Q minus the maximum degree. So this will take care of this first term. The second term is literally a projection matrix. So it has operator norm 1, at most 1, because this vector here is designed to have L2 norm 1. So you can see this is maybe where the square root comes up, which is that this vector has L2 norm 1, so we're projecting onto the orthogonal complement of this vector. This is a projection matrix. And this third vector is maybe where something more interesting is happening. So what is this third term saying? So this is the Hadamard product. So I take the entry-wise product of the probability that my root vertex is colored C times the probability that my neighbor is colored C. Let's just consider some examples. Well, if this neighbor is colored C, then this entry is 0. The corresponding entry here is 0. So the entry-wise product is 0. Right? The entries of this are just kind of the probability the root vertex is C times the probability that my ith neighbor is C. So since they're mutually exclusive, in fact, if one of them is 1, one of them is 0, but also this is controlled everywhere in between. Because basically these two quantities are anti-correlated. As this one goes up, this one goes down. And so what this says is that we can kind of get some global control on how big this function can be by just choosing a potential that kind of combines them in a way that magnifies this anti-correlation. And that's really the main idea that allows us to show kind of this type of contraction.
So you need, for the norm, so two is projection, you don't care about it. You want to get 1 minus delta.
Yeah.
But already the first one gives you something better.
No, there's an inverse here. So you're getting something bigger than 1 here.
Oh, inverse, very good. Okay, now that's explainable. And then that means that it has to be pretty delicate.
Yeah.
Just to get 1 minus delta, it's not I mean, if you get something bigger than 1, you want to scale it, and if it went to 0, it would be really weird, so.
Yeah, in fact, it does, so in fact, one thing is that like, what I wrote here, I'd like doing a little bit of lying, which is this argument works as is, if the number of colors you have is at least delta plus 3 root delta. Because this is like really not very much bigger than 1. And you have to do something more clever to get all the way down to delta plus 3. And what you do is you basically take some more complicated norm where you look at each of your neighbors and you like figure out which one are your bad neighbors and which ones are your good neighbors, and you do some reweighting. So it is actually, it gets delicate, especially you can imagine like the bigger and bigger this is to actually make sure that you get the cancellation.
Is that just a better choice of phi or not?
No, same choice of phi, different choice of norm. Right, like the norm that's being used here is just like the max 2 norm. And so you have to do like kind of a weighted like a weighted 2 norm where like you weight your neighbors differently. Other questions? These are really good questions.
So the global correlation is going to be, anyways, even for delta plus 3 or with delta, you want to get, you will get what? You will get 1 minus some other constant time with delta. I mean, it would be, I mean, you get back to just below 1 and not more.
Yeah, exactly.
So-
You end up like, it's actually kind of funny because you'll notice that the conjecture is that strong spatial mixing holds when Q is at least delta plus 1. And we get delta plus 3, which is essentially, we have some, arithmetic calculation that needs to be less than 1. I think technically we get like 2.7 or something, but like unfortunately colors are integers. And so yes, it does actually become something, it becomes like some actual numerical expression you get on this side. But you get very strong anti-correlation.
Yeah, it was not obvious that it would
No,
not come up a little above 1.
no, not at all obvious.
Yeah. That's despite that you take some worst case over these
Yeah.
correlations. They are anti-correlation.
Yeah, basically you need to kind of show that you make progress no matter what this marginal distribution looks like. And then when you're getting really close to Q equals delta, you need to kind of show that like you need to weigh these i's appropriately so that depending on how skewed their marginals are, you're weighing your progress appropriately so that you're always continuing to make progress. Other questions? Okay, then maybe the last few minutes, I'll tell you a little bit about result number 2, and why it's a little bit surprising and how we make progress. In order to do this, I have to tell you a little bit about how we actually prove that you can optimally sample. And we do that by showing.
So for number 2, you're not assuming it's a, you're not assuming it's a tree.
No, this is for all bounded degree graphs which have sufficiently high girth. And so what we're going to do is we're going to show, I think kind of like an interesting thing is what do we actually do in this proof is we exhibit some property, which is that, kind of we get contraction. And what we show is that this implies a variety of lovely properties we care about. One of them is strong spatial mixing. Another of them is this related notion called spectral independence. Now, obviously, because we only prove strong spatial mixing on trees, we will only get directly whatever this consequence is for trees. But one kind of, I think, very interesting question is that it's kind of believed that there are a lot of like implications you could prove directly, for example, from strong spatial mixing to spectral independence. And these kind of things are like generally not known. But what turns out to be true is like most times when people write papers, whatever they prove proves like, some, large collection of these properties all at once, even though none of them are known to imply each other. It's basically believed that all of them are equivalent. So let me tell you what spectral independence is. So in order to do that, let me define the influence matrix. So this is another notion of correlation decay, which is that the influence matrix is some matrix, which I'm going to define to you by its entries. So it's the influence matrix of a distribution U, and it's the influence of assigning vertex U to be color B on the probability that vertex V is colored C. So as long as you think about it that way, it doesn't really matter what the formula is. And so it's the probability that, maybe I'll just write it this way. The probability that U gets the color, vertex V gets to be color C, given that I told you that U is V, minus the unconditional probability. right? So this is just saying how much influence does assigning vertex U to be color B have on the probability that vertex B is colored C? And we'll say that distribution mu is big O1 spectrally independent. That has the word spectral in it, so a condition is about to arrive that looks spectrally independent, if the maximum eigenvalue of not just this influence matrix mu, but in a way that should remind you of strong spatial mixing, but the conditional influence matrices is big O1 for all pinnings. So if I have that these influences have bounded maximum eigenvalue for all pinnings, then I say that a distribution is big O1 spectrally independent. Okay, and very beautiful work over the last few years, you know, in large part due to my collaborators, Kuku and Zunchen, shows that if I exhibit this property, which is a property of the distribution, that is sufficient for me to get black box sampling results. So this is Inari. Okay, so various folks.
Those of you who want, there are several talks that were given here about 2-3 years ago by Anari, by Shayan, by Garan, and by Liu. Here on the video, you know, on our video channel.
Yeah, so I'm going to state this just in the context of Q colorings, even though a much more general result is no, which is that if mu is big O1 spectrally independent, which I'll abbreviate to SI, and has bounded marginals, which it does, then Glauber mixes in n log n time. So now maybe I've convinced you by drawing this very rigorous picture here that we get spectral independence on trees, but I still haven't said anything about how do we get any result on high girth graphs. So let's start by taking an initial stab on how might we prove spectral independence on high girth graphs. All right. So what's good about a graph being high girth? It's not like locally, it looks like a tree, right? This is like really like, you know, maybe where we might start. And so if we like kind of took our initial stab at trying to prove, kind of imagine we really wanted a spectral independence result on trees. Well, what we could prove is that, you know, I take my graph, it has girth G, which means that the first, you know, roughly girth over 2 neighborhoods, the induced subgraph is a tree. And now if I just apply black box, my strong spatial mixing and spectral independence results on trees to just this, you know, graph, then what would I get is I would get something like, you know, the kind of, if I look at, you know, tau and I look at some tau prime, and the total variation distance is like 1 minus delta to like the girth over 2. Okay. Unfortunately, we want to assume that the girth is constant, not growing with the graph. And so this is not going to really help us very much unless the girth is actually growing with n. So we will get some kind of mixing result, kind of a weaker mixing result because it's a polynomial, as long as the girth is log n. But we really, really want to prove this result when the girth is only a constant. And so we have to do something smarter, right? We have to do something smarter than just trying to study, you know, just literally saying that some subgraph of this graph is a tree. And so this is the main idea of what we actually do, which is we show that our kind of Jacobian contraction result actually implies a much stronger correlation decay result on trees than strong spatial mixing. And that even though maybe, I mean, we think it is sufficient to have strong spatial mixing on trees, but in fact, this very strong spatial mixing or very strong correlation decay on trees is enough to get this result on high growth graphs. And what is this total influence decay result? Well, I'm not going to be too fussy about the definition, but what it says is that the total influence of vertex V on its distance exactly equal to k neighbors is at most 1 minus delta to the k. Why is this stronger? Well, this is stronger because I could have exponentially many in k distance k neighbors. Strong spatial mixing just says that the influence of each of my neighbors is like 1 minus delta to the k. But this is saying the total influence I have on all of my distance k neighbors is in fact also decaying exponentially.
What is the difference in terms of the?
in terms of this sense. But all of these are relatively similar to each other. So I can actually write formally what the definition is. Which is that like, let's say I said mu, let me definition. Mu has total influence decay with rate 1 minus delta. If it's the case that the sum of all of the vertices, so I'm going to use SUK to be the sphere. So this is the sphere of which I mean exactly distance k, of distance exactly k. If I just literally add up the kind of difference in marginals, so mu v, kind of for all pinnings. So the total influence when I make UV minus when I make it some other color C, if this thing is decaying exponentially.
It seems that it's so long, it seems like it would be enough to have distance 1, because you want to continue, right?
Well, this thing will have, I mean, over here,
Yeah.
you have this K here, so it's
Yeah,
not
I
enough.
understand, but you want to use this to continue, and you don't neutralize them up over exponentially many, right?
Yeah, I think it's not obvious that this is even enough though, because what this says is we're bounding is the total variation distance. So we're saying that it's unlikely that you have disagreement, but when you do, when something goes wrong, we have no control over how badly it can go wrong. So you can think about like kind of the fact that like, even though we're saying it's unlikely over all your neighbors, that your kind of total, like your total influence is small, when you have influence, is it just that like kind of there's a little bit of difference? Or is it the case that they're wildly different? That's the problem with this TV distance, right? Is it's bounded by 1. So it kind of doesn't control what happens when things go wrong. Kind of your disagreements can still proliferate out of control.
This is still for trees.
This is for trees.
Yeah.
And so, kind of contraction implies total influence decay on trees. Yeah, so we still need to get to graphs. But this turns out to be the important necessary ingredient to getting to graphs. And so what are we going to do on graphs now? So now we have a graph, it could have cycles, but we're still going to use the fact that it locally looks like a tree, and we're just going to try and bootstrap ourselves. We'll use the important fact that the maximum eigenvalue, we're trying to show spectral independence. So the maximum eigenvalue of the influence matrix is at most, so this is at most kind of the maximum over all my vertices U that are not pinned of the one Wasserstein distance, which is just, I'll actually write some kind of, this actually looks a little bit different because this is a distribution on almost the rest of the graph. So if I take some coupling, so what am I saying here? Well, we want to bound this maximum eigenvalue of the influence matrix. This is at most, you can do some calculation and check that this is at most the expected Hamming distance that happens when I couple these two distributions together, which is in one case, I pin U to B and I just look at the induced distribution on the rest of the graph. And in the other case, I pin U to C and I look at the induced distribution on the rest of the graph. And maybe that comes back to your question, because what will happen is like, total influence decay naively will say that, oh, it's very unlikely that, kind of these two vertices disagree. But when they do, the kind of Hamming distance they can cause can go up by a lot.
The Hamming distance on the distribution.
Pardon?
What's the Hamming distance?
This is the Hamming distance like you can think of in coordinates. I take two couplings. And so these couplings, if I sample from them, I'll just get some coloring. So I'll just like count how many vertices these two give me different colors on. And we want to show, this is what we want to show. We want to show this is big O1. Okay. And so the way that we actually prove this is we use a recursive coupling. So what we say is, let me kind of look at two copies of my graph. Here U is B, and here U is C. And now let me pick some K. Okay, let me try optimally coupling the distance exactly K neighbors. In the good case, I succeed. These both agree. Even though U is B and U is C here, they succeed. Okay, and so my expected Hamming distance is at most the probability of this good case. And when this good case happens, any disagreement is contained above here because these two agree, hereafter everything will be the same. Times delta to decay. And now what happens in the bad case? Well, when I'm doing this coupling, let me just randomly reveal the colors of the vertices in these neighbors one by one. In the bad case, I reach some vertex V. And in this case, V got color B prime. And in this case, unfortunately, V got color C prime. So this is the sad case. But it turns out what we can do is we can just use the triangle inequality to say now the expected Hamming distance between this one and this one is like the sum of two cases. So now what we get is that the Hamming distance, right, the kind of distance, kind of this distance between kind of U goes to B and V goes to B prime, and U and mu of U goes to C and V goes to C prime is at most when I just changed the pinning one by one. So it's at most you can think of as like twice E. And so then I have the probability of the bad case times twice E, because you can just do this triangle inequality to first change this U to a C, and then you can change this B prime to a C prime. And why is this really good for us? Because now we only need to show that the probability of this bad case, rather than being exponentially unlikely, which we would need like logarithmic girth for, we only need to show that this probability of this bad case is at most like a half, right? As long as this is strictly below a half, we will make progress and we'll be done. And essentially, if we just apply total influence decay on trees, and we choose K to be something smaller than the girth, we'll choose K to be like log delta, and then this recurrence can kind of iterate for log delta steps, then that will be sufficient.
So yeah, I was wondering before why K, for this type of argument, for you're using I mean, even, it seems like even K equals 1 may be enough.
I think when K equals 1, you just don't get enough.
What is this relation between 1 minus delta and 1 minus little delta and delta?
Yeah, that's right. So you need this like little delta to become like, you kind of want this to hold like 1 minus K log, something like this. You need, there's some like, you know, kind of set of parameters that need to all work. But the point is that if we take K to be roughly log delta, as long as the girth is roughly log delta squared, we'll kind of be in good shape, because by the time we go log delta steps, the probability of this bad event has gone down to like a half. And this is a key idea, which is that even though kind of the one-shot coupling doesn't work, you kind of can find, i.e. like just looking at one small tree-like piece doesn't work. If a graph has large girth, it has lots of little tree-like pieces. So as long as you find all of those and you put them together, you're able to make progress. Cool. That's all I have, if people have questions.
Thanks. Question, yes.
Yeah,
So what's the dependence of the spectrum dependence parameter on delta?
that is a good question. I do not know exactly off the top of my head. It is, I think, let me get back to you after the talk. I will just tell you something wrong now.
That will affect the mixing time.
So the mixing time, this is a good question, but this black box reduction of the mixing time has the spectral independence parameter not go into the exponent of n, but it actually goes into this constant in front of the n log n. So this is like the really beautiful thing about this paper. So I think it's something like singly exponential in delta. But like I said, I have to double check. I'm going to just tell you something wrong now.
This reduction is one that gives the high dimensional expander. Then there's the appearance of this spinning tau, which is for links in the high dimensional expander. Although Ronen has a framework which does not seem to use the high dimensional expander. So there are other proofs.
Yeah, the stochastic localization, but naively the spectral independence constant goes into the exponent. For graphical models like Q-colors, you can actually pull it out into the constant. Yeah?
Can there be a different dynamics that would converge in linear time?
Yeah, for the right notions. I think, like, for example, you can learn these like parallelized kind of Glauber dynamics if you make like pretty non-local updates. But I think that I think that kind of for most algorithms, it's expected to n log n. I think if you can define models where linear is like, I guess the computation time, I think like some of these parallelized models converge in linear steps, but I think they maybe take a long time to update.
You can, the coupon collector bottleneck is very easy to overcome. I mean, you can make maybe pick a random permutation of the vertices and run through it and do it, 100 times.
But does that,
And then you won't have the problem of missing a vertex.
but we have no idea if that.
No, I don't know how it works.
There's no obvious reason why that shouldn't.
There's no reason I know.
Even with entropy methods, you still have to pay like log of the initial.
No, you cannot.
Yeah, that's right.
No, but you're right, but if you are not touching some vertex, if you are picking vertices independently, doesn't matter what you do, you will miss vertex. And so you will not change the initial current. So you have to eat. Like I said, you have to eat every vertex at least one.
No, but what I'm saying is like for the entropy methods, like usually the log n comes from like log of the state space.
Yeah,
So
Yeah.
even if you did like a permutation of the states, I still don't see how you would get rid of the log n.
I see, you went on in the other way, sorry, I didn't answer your question. So,
Yeah.
Yeah,
like the mixing time usually has this parameter that if you use like Dirichlet forms, it's like log of the state space. And if you use entropy methods, it's like log, and I think that will still induce this log n, because it'll be log of 2 to the n or something exponential in it. But yeah. Yeah,
In the general results, the structure spectral independence implies fast mixing. I think there's also assumption of bounded degree, so.
yeah. So that's, I was working really with the setting of mu,
Oh,
which is like, for Q colorings on bounded degree graphs. Like, it does work in general for bounded degree, bounded marginal graphical models.
Another question is that you said the total influence decay is like a stronger version of strong spatial mixing. Is that rigorously known or?
Well, I think we think they're all equivalent, but it is like you can imply strong spatial mixing from some notion of total influence. So I think like basically it's believed that all of these are equivalent, whether or not they sound stronger or weaker.
Thank you.
so what is the extent or generality of this, new new notion of total influence decay? How, well, maybe you said it there, how, in what generality of, global dynamics systems can you see or it makes sense only?
I think basically for this like Q colorings model, once you have this kind of contraction proving total influence decay, like you can pass through something like spectral independence on graphs, but I don't actually know what else you could conclude directly black box. It is like kind of nominally able to prove things that it's not clear how to prove with just these two. But yeah, I don't know. That's a good question.
One question. All right, thanks.